Welcome back to the AI Research Roundup. I am your host, Alex. Today, we're diving into a really interesting paper from the Papers with Code trending list. It's called RKV, which stands for Redundancy-aware KV cache compression for training-free reasoning models acceleration. So the core problem this paper tackles is that when AI models perform complex reasoning, like with chain of thought, they generate a lot of text. This creates a huge memory bottleneck because of something called the key value cache. You can think of the key value cache as the model's short-term memory. It stores context from previous steps. The author's solution, RKV, smartly compresses this cache by identifying and reducing redundant information. And the results are pretty stunning. They achieve nearly the same performance with only 10% of the original cache size, leading to huge memory savings and a massive speedup. We'll get into the details of how they do this in a moment. And before we dive into those details, what's really great is that the authors have made all the code for this work public. The repository has everything you need to get started, including the core RKV package and evaluation scripts. They even provide a notebook for visualizing the token compression, which is the process of reducing the data for each unit of text or token that the model processes, so it's very accessible for anyone wanting to experiment. Alright, so this figure gives us a great high-level view of how the RKV framework operates. On the left, you can see the overall process. As the model decodes text, its short-term memory, that key value cache, gets bigger. Then, the RKV method kicks in and compresses it. The real innovation is in the middle section. It simultaneously calculates two things. First, it measures redundancy using a technique called cosine similarity, which basically checks how similar different pieces of information are. And second, it calculates importance using the model's own attention scores, which tell us what the model is focusing on. It then combines these scores to decide what to keep. And this figure really drives home the point about redundancy. It shows a model solving a simple math problem. What percentage of 30 students is 3? And you can see in its internal monologue, these think steps, it just keeps repeating the same conclusion over and over again. So 3 students are leaving early. A method like SnapKV, which is shown here, only looks at those attention scores we talked about. It ends up keeping a lot of this repetitive information, which is exactly the kind of inefficiency RKV is designed to eliminate. And these charts really quantify the problem we just saw with that math example. On the left, we're looking at the average length of the model's response. You can see across both the Math 500 and AME 24 datasets, the models generate responses that are way longer than the ground truth, which are the ideal human-written solutions. Then, the charts on the right look at repetition. They measure the frequency of 1 gram, which are just single words, and 2 grams, which are 2-word phrases. And again, the models show a much higher frequency, meaning they're repeating the same words and phrases far more often. This data shows that model-generated reasoning is not just long, but also highly repetitive. So after seeing just how repetitive these models can be, these charts show us the real performance payoff of tackling that redundancy. We're looking at 4 scenarios here, with different models and math datasets. The horizontal axis is the key value cache budget, basically how much memory we allow, and the vertical axis is the pass at 1 accuracy, which just means getting the right answer on the first try. The green line at the top, full KV, is our baseline. No compression, full accuracy. Now, look at RKV in blue. It consistently gets much higher accuracy than SnapKV in orange for the same memory budget, and it nearly matches the top performance of the full model while using only about 10 to 20% of that memory. This is a massive efficiency gain. Okay, so after seeing those big wins, you might be wondering how RKV gets that balance between redundancy and importance just right. These charts break that down. It all comes down to a key setting, a hyperparameter, that they call alpha. You can think of alpha as a knob that tunes how much the model cares about redundancy versus attention. On the left, you see the internal score for each token. The brown line is attention only, while the blue line is redundancy only. The other lines are RKV with different alpha settings. Then the performance chart on the right shows what really matters. Pure attention or pure redundancy alone don't perform best. The sweet spot is the green line, with an alpha of 0.1, proving that the best strategy is combining both metrics. And this figure gives us a great visual for what that combined strategy actually looks like in practice. On the left, with SnapKV, the model gets stuck on an incorrect thought, and you can see it keeps selecting the same few repetitive phrases. It's fixated on the wrong path. But look at RKV on the right. Because it's aware of that repetition, it selects a much more diverse set of tokens, capturing the initial problem, the key calculations, and the final correct answer. It's not just keeping the loudest voice, but the most important steps in the conversation. Alright, so after seeing the quality of what RKV keeps, this table puts some hard numbers on that performance boost. We're looking at the Llama 3.8b model here, comparing memory savings, decoding time, and throughput, which is basically how many text tokens the model can process per second. The results are pretty staggering. For example, with a 90% memory saving, RKV boosts the throughput from around 850 tokens per second for the full model to over 3,800. That's a speed up of more than 4 times, all while using a fraction of the memory. What RKV shows us is pretty profound. It's not just about keeping the tokens that get the most attention. By also identifying and removing what's redundant, the model can reason much more clearly and efficiently. This training-free approach makes large models dramatically faster and less memory hungry, which is a huge step forward for running complex reasoning tasks on more accessible hardware. And that's all the time we have for this week's AI Research Roundup. Thanks for tuning in. I'm your host, Alex.